magnets are not only a topic to cover in physics, but have many real and practical applications. As you see here, magnets even play an important role in pop culture with the X-Men character Magneto and his ability to shape and manipulate magnetic fields that exist naturally or artificially. As you may recall, in Chapter 20 we learned all about magnetism. So let's discuss what we already know. We know that like poles, as shown in the short video, repel, and unlike poles attract. We know that if you break a magnet in half, the new halves will each have a north and south pole, and so on if you keep breaking the magnets in half. In other words, the magnet keeps getting smaller and smaller, and each one will have both a north and south pole. Finally, as you can see in the diagram, we know that magnets produce a magnetic field that never intersect, that form closed loops, that point out of the North Pole, and outside the magnets, the direction is from North Pole to South Pole, and inside the magnets, the direction is from South Pole to North Pole. We also know how magnetism is generated from the charge in motion as electrons move around the nucleus and spin. Many people may know more about the electron spin from the topic being discussed in their chemistry class. As shown in the short video clip here, the ability to make objects suspend is quite popular, specifically as desk decorations. Magnets are also used in many objects, like MRI machines, credit cards, TVs, and to merely stick notes to your fridge. However, our current understanding is now changing due to a new discovery by researchers. As stated, we found a published article detailing how physicists found a brand new kind of magnet hiding in a uranium compound. Let's quickly summarize the article to learn what they discovered. Physicists recently did a ton of research and discovered something really cool in USB2, which is a compound of uranium and antimony. The new type of magnet differs from the type that we learned about because it is singlet-based. In the new magnet, the electrons arrange themselves to form what is called spin excitons. These spin excitons are quasi-particles. The spin excitons are what make the singlet magnet produce a magnetic field. Let's now review what we know about magnets and what some of the differences are with this new type of magnet. This diagram from the article helps depict the differences in alignment between the typical magnet that we learned about and this new type of magnet. As stated in the article, in singlet magnets, the magnetic field doesn't result from a large group of chaotic magnetic fields suddenly aligning, but rather from the appearance of a new kind of magnetic field amid the existing particles. But why is this important? Let's discuss the practical applications that this new magnet has. Data storage and technology are rapidly expanding, and this new magnet could help with these areas because it can flip between magnetized and unmagnetized much quicker than regular magnets. The flipping between magnetized and unmagnetized is what many computers use to store data and operate. There are lots of expanding career fields that have to do with data storage, and these new magnets could play a big role in that field. All information was generated from our lecture notes in Chapter 20, Magnetism, and the published article as listed here.